Good afternoon. It's a pleasure to be here. I've been hanging around here for about a month as part of the workshop, and really appreciate the opportunity to participate both in the workshop and this conference. So I thank the organizers for putting together such a nice program. So I'm going to tell you a little bit about some work that is still ongoing, but towards the end. And the work is with John Toner, and it's about Coulomb interactions and actually super Coulomb interactions. We're still looking for a better title, but interactions in two-component plasmas that are longer range than Coulomb. So it sounds maybe slightly less physical, but if you think about spin systems that we've been hearing about and various engineering systems engineered in degenerate atomic gases, ultra-cold atomic gases, either systems with dipolar systems with molecules and atoms, or resonant Rydberg states. There's a lot of interest. This conference is an example of that, and the workshop as well, in systems where there's long-range interactions. There's also systems where you can have, use cavity modes, phonon-mediated exchanges, as we've heard about, where one can also engineer effective long-range interactions with a variable exponent. And so that's a second type of motivation that we've heard about, but maybe something that you've heard. If one looks at effective theory, long wavelength theory of a surface, some modes in the surface that are coupled to a gapless bulk, then the effective field theory on the surface has effective long-range interactions that are induced by and mediated by the gapless bulk modes. And so there's depending on what the bulk modes are, you can engineer various types of long-range interactions on the surface. So that's another class of motivations for what I'm going to be talking about. This is the outline. So I'm going to introduce this super Coulomb gas, and by super I don't mean anything about superfluidity. I just mean maybe it's a bad choice of a title of something that has interactions that are longer range than Coulombic. Okay, and you can be the judge of, or experimentalists can be the judges of how interesting it is from the physical point of view. So think of it as just it'll be a mathematical result that I will prove. Okay, something about these kind of systems. So I'm going to then discuss two ways of treating kind of a two-component plasma, and then relate it to something that's of interest in this conference with systems with a long-range XY model and magnetic systems with long-range exchanges. Okay, so but before sort of I launch in, it's good to think about so what I'm really interested in is how this kind of a long-range super Coulomb or long-range two-component plasma screens. Okay, and we know in nature you could have some microscopic interaction that has certain range or certain property, and what we really want to know is once you're not in a vacuum, what happens to that interaction on longer scales. Okay, and let's look at some examples that we're familiar with in nature. So one familiar one is if you have a plasma, the charges are conducting, they can move around freely. So then, you start out with Coulomb, but at longer scales beyond some screening length, you buy Huckel screening length if it's a thermal one, or Thomas Fermi if it's a degenerate system, you get Yukawa-like interaction. You have exponential-like interaction with some decay length. Okay, so you can think of these systems are conducting, they have a infinite dielectric constant, so the charges are free. And so this is kind of a depiction of that. The other type of screening is in a dielectric, meaning an insulator. So you have, charges are bound into pairs. They're not free to separate, but they can, they can polarize into dipoles and screen the effective electric field. And so there you go from, let's say in 3 dimensions, 1 over r Coulomb to 1 over r, and it just gets reduced by a finite amount. Okay. The other ones are a little bit maybe, familiar from particle physics, standard model, QED. You have a you can think of it as effectively at long scales, you have a dielectric constant due to electron-positron pair production, or, polarization that also screens it at long scales. You get reduction of your actual effective screening, so effective charge is logarithmically reduced. And, you can think of it as a dielectric constant that's bigger than 1. And it's actually flowing, it's length scale dependent. In QCD, it's the opposite. At long scales, things become stronger. Okay, so this is just sort of as a background to get us in the mood. And again, so let me reiterate. So I'm going to consider systems that have, sort of a two-component plasma, so charges can be positive and negative. They're interacting with some bare interaction, U naught. And for Coulomb, that's going to be, just to have a notation, what I mean by Coulomb is in any dimensions, 1 over q squared. And so then in real space, it's going to be 1 over r to the d minus 2. Okay? And with some coefficient here, which is, proportional to charge. And so that's the picture, and what we know is what I just already said. You start with the bare one, but in the dielectric, it's going to be screened down a little bit by some dielectric constant, having to do with polarizability of these pairs, of these dipoles. Okay, so now what I want to consider is, this longer range than Coulomb interaction. The Hamiltonian is the same, but now there's going to be some r to omega, or you can think of it as r over, omega can have either sign, and so that's going to be part of the richness of the problem, but, sometimes I'll write it with a positive sign, positive form like this, but then, in your mind, you're going to have to flip omega is positive or negative, and I'll consider both cases. But I think for conceptually, it's easier to think of a bare interaction as having positive omega, because I want to think of a system in which there are dipoles, charges are bound into pairs. Okay, and so what does it mean longer range than Coulomb? I just mean that omega is 2 minus d plus sigma. So it's stronger than, it grows stronger than sigma. And again, so like if we were in 2 dimensions, sigma, let's say Coulomb sigma would be 0, you get a 0 here. 2 minus 2 is 0. That's the log interaction, of Kostelis-Thales that we know about. If for 3 dimensions, 2 minus 3 is minus 1, so this is 1 over r for sigma equals 0. But with positive sigma, it's going to be slower than 1 over r. That's the kind of thing I want to think about. Okay, so that's the system. And again, what I want to know is I want to think about what happens for positive omega, for example, when you consider screening. And so I'm going to give you a result, because I tend to ramble and run out of time, so this is the punchline. So the kind of, if you wish, a theorem, a physicist theorem, you start out with this kind of a super long range interaction with some non-zero sigma microscopically at a long scales longer than some screening length. It goes back to Coulomb, 1 over r to the d minus 2, and the role of r to the minus sigma is now played by the screening length. So it's a very clean thing, so it's just basically, dimensionally you see these are the same, but now the anomalous long rangeness gets taken over by the screening length. Okay, so that's the result, and everything else is kind of, I'm going to just explain where this comes from, and it turns out it's a lot richer than we originally expected, having to do with a sign of omega, dimension of space being bigger than 2 or less than 2, positive sigma or negative sigma, which is going to modify this kind of a, plain vanilla answer, okay, in those different regimes. Okay, so one prediction is the value of this screening length. It depends on the K, the bare K, divided by temperature, and the fugacity or the core energy of these charges.
Do you mind?
Yeah, no, I don't mind.
Sorry, but if I don't ask the question now, I think I won't understand it. But shouldn't the screen-Coulomb interaction be exponential, like Yukawa?
No. Okay, so screen is a bad word. In this case, it's really, you should think of it as a crossover scale between this and this. Yukawa is on, that's why I reviewed the Bihaka theory. Yukawa happens when you have free charges. And there will be a regime like this when I get into the talk further. And it depends on the dimension space and the sign of omega. So I'll get there, but that's the...
So this is like a medium, like a...
Yeah, no, I mean, this is why I warmed up with this case, right? So if you wish, it's like intermediate between it's intermediate between this case and this case. This is Yukawa, and this is just trivial, just rescaling. But this is something in between. It actually changes the power, okay?
So now I understand the picture
Okay? So notice here, I very slaved over this picture. You know, there are free charges here. Here, there are only dipoles, so this is very different screening. Okay? One is a conductor, one is an insulator. Okay? Okay, so, yeah, so we calculate this guy. Notice it goes in the right direction. It goes as some lattice scale, some UV scale. The stiffer the charge and lower the temperature, the longer this crossover will be. And also there's some fugacity. The bigger the fugacity also for the charges, the longer the scale is. Okay, so this, you can reason out that it goes all in the correct direction. But, if you wish, the main result is on this slide. Okay, everything else is detail. This is sort of a visual representation of the same thing. You start out with some, let's say omega is positive, you start out with some binding potential microscopically as r to the omega with a sigma in there, and then it crosses over to 1 over r to the d minus 2 if d over 2, so you can think of it as now no longer binding if d is bigger than 2, or it will be binding if d is less than 2. So those are, for example, two cases that will be important. Okay, so let me just give you an idea where this comes from. So this work is extremely elementary, so there's no sophisticated field theory or anything like that. So everything I'll say is just, you can really understand real time, I hope, okay? So there's not a lot under the hood, but, just to give you some idea where this comes from, you just generalize standard dielectric. One way to derive it is you just generalize standard dielectric analysis to this problem. And the cool thing is, the result is very simple, but it's kind of, if there's a physical systems like this, it's quite impactful in that it tells you this, that's why I call it Coulomb universality. It tells you no matter what sigma is, if you find if you have a problem that microscopically has a sigma, you will revert to having sigma equals 0, namely Coulomb at long enough scales. So again, how do we do dielectric? Well, we say, what's the effective potential? Here's the bare potential. Well, you have to add the potential generated by the induced dipoles that come from this potential, from the overall potential. So here are the dipoles. Well, what is this induced potential? It's going to be electric field of this bare potential, and you think of like some external charges, times the induced dipole moment, integrated of all possible dipole moments. Okay? Not all dipole moments, but integrate over all possible locations of that dipole moment. That's what I mean. Okay? So, but what's the dipole moment? Well, the dipole moment itself is induced by the actual local potential U. And so it's given by electric field of the actual potential, the actual electric field, times some susceptibility, electric susceptibility. And we computed that electric susceptibility. And it's finite if your system is dielectric, meaning the potential omega is positive, the potential is binding. So that, if you put in a little bit of electric field, you're going to get bigger dipole. So it's linear in the electric field. So literally you take this guy, you stick it in here, and you Fourier transform, and lo and behold, you get an expression like this. So now let's analyze it. This is the bare potential, this is the effective potential. Well, first, let's analyze it for standard Coulomb interaction. Just a sanity check. If U naught is 1 over Q squared, you have 1 over Q squared here, you have 1 over Q squared here, Q squareds cancel out, so you get 1 plus chi times K. That's your dielectric constant, so you just get 1 over Q squared divided by some constant. That's the usual result. But now, imagine this is no longer 1 over Q squared, but it's logarithm than 1 over Q squared, so it's 1 over Q squared, 1 over Q to the 2 plus sigma. So now when it's multiplied by Q squared, this thing is actually divergent. So it beats the 1. U naughts cancel, and what you get is 1 over chi times Q squared. And that happens when this term, which is growing with small q, is bigger than 1. That's the crossover scale. And that crossover scale is just directly related to chi. And so that's the coherence length, or crossover scale, or screening length scale that I showed on the previous slide. And so then you get this result. 1 over Q squared that you generate then translates into this in real space. That's really as simple as this. Okay, there's nothing more. It took us a little while to actually get this, and it really comes down to calculating the susceptibility, and that's slightly technical, but still conceptually very simple. Let me give you another derivation of this, which is kind of cool, and gave us more confidence that what we got is, the dielectric analysis is actually correct. And that's having a different approach using Sine-Gordon, RG. So once you understand this, then it's even more trivial than the dielectric analysis. And it's kind of really revealing of, why this is, why Coulomb is so universal. So you start out with some kind of this gas, this two-component plasma. But what you can do is you can convert it into a Sine-Gordon model, and that's well known. So you basically can decouple it with a Hubbard-Stefanovic field theta, and then, introduce fugacity, and basically you can turn it into the Sine-Gordon model. Normally you get a gradient of theta squared, or q squared theta squared, but here, this long range in u naught with a sigma in there becomes q to the 2 plus sigma, okay, plus a cosine. Okay, the cosine encodes the discreteness of charges, okay? And so here's the expressions for this k tilde and g. Okay, so now what you do is you simply take and do coarse grading. You integrate out some short scale modes and ask what's the effective theory on the longer scale. So that's the RG you end up performing. And what you discover is immediately that you produce, very generically, you produce another term, which is kappa q squared times theta squared. Okay? And so now immediately you see what happens. If sigma is positive, this term is less singular than this term at long scales. So then this guy dominates, and there'll be a crossover between this term and that term. And that's the screening length. And this q squared is the embodiment of Coulomb interaction when you reverse this process. So, this guy, or this guy, means longer range than Coulomb with a sigma, but q squared represents Coulomb if you integrate theta out. Okay, so this crossover in the Sine-Gordon model from q to the 2 plus sigma to q squared is the crossover from longer range than Coulomb to Coulomb. That's all. It's really as simple as that. So now really we want to just calculate this kappa, and for that you need to do RG. There's flow equations for k tilde, which is fairly simple. It's just set by omega because it's non-analytic interaction, so it doesn't get renormalized. Then G flows, the coupling of the cosine, the charge fugacity. And then the key point is kappa flows. In this non-trivial way, you solve this set of equations and you find the effective kappa that depends on the length scale you look at. And the key observation is if you send the length scale to infinity, L goes to infinity, you look at the largest length scales, this thing just saturates, and it saturates at some constant that I give here, and that constant is the effective kappa that you see beyond the screening length. And that kappa, if you use now this kappa to reverse this steps to give you the two-component plasma, you'll get exactly the coherence, or if you use this kappa to calculate the coherence length, or not coherence length, but the crossover scale, C, which is determined by when this term is comparable to this term, you'll get screening length, which is exactly the one, to the two numbers of order 1, it's exactly the same screening length as I described in the Debye-Huckel theory calculation. Not Debye-Huckel, in the dielectric calculation. Okay? So that's in terms of derivation or results, that's sort of the basic results. So now let me try to summarize it for you. And then as you start summarizing, you realize, well, there's actually, problem is a little bit richer than what I've just summarized so far. So let me present it in a couple of ways. It's a little bit, can be a little bit confusing. So positive sigma is longer range, negative sigma is shorter range than Coulomb. And this is the dimensional space. And I should actually say, let me go back for a second. Well, let me go to here. So notice if sigma is negative, as a byproduct of this result, if sigma is negative, then this term is less singular than that. That means shorter range than Coulomb does not get renormalized. Okay? So if it's shorter range than Coulomb, then that remains. Second observation is, well, same observation in this dielectric analysis. If if the bare interaction is less singular than 1 over q squared, then let's say 1 over q squared, q to the 2 plus something, then, sorry, minus something, so it's less singular, it's a long scale, then this term is always smaller than 1. And then your bare interaction is not renormalized. So positive sigma and negative sigma behave very differently. Positive sigma gets screened down to Coulomb. Negative sigma does not get screened, and you get this non-universal sigma-dependent answer. Okay? Yeah.
What happens in the limit when sigma becomes d minus 2?
Yeah, so I'll discuss that. Then it's all to all.
It's all to all, so you can't screen anymore because you don't have a length scale.
Let's see.
You can't have screening in that limit.
Yeah, I need to think about that special case. It's, but maybe next few slides will describe this. So I'm going to describe all the cases, and maybe one of those cases is that in particular. Okay, so.
Okay.
Yeah, so let me delay that until we go through these. Okay, so this is why I'm considering positive and negative sigma, and then as a function dimension. So positive and negative sigma is clear. I want to consider a possibility of screening or not screening. That's important. The other, the dimensionality space is important because depending on whether G is bigger than 2 or less than 2, determines whether the bare potential Coulomb potential, corresponding Coulomb potential, is binding or not binding. Clearly, I have to do different things. If the bare potential is not binding, that means the charges are actually at finite temperature will be, unbound, and then you have a plasma. While and that happens for D greater than 2, but if D is less than 2, then it's a stable dielectric because, the bare potential is binding, and this guy is negative. Okay, so the other key point that I already mentioned is another line through this sort of phase diagram is omega equals to 0. Omega positive means the bare potential is binding, meaning it's a dielectric. You can think of it as there are no free charges, even at finite temperature. And negative omega means the initial problem is not really, treatable as a dielectric. It's really a plasma at any finite temperature. So those are two different regimes, okay? And then, of course, like I said, D equals 2 is special. To the left and to the right are different. And then I try to just label them in my maybe awkward way by B naught and, B and U. So the first letter represents, for different regions, first letter represents, is the bare guy bound or unbound? The charges are bound or unbound. And the second one is where the screened one is bound or unbound. Okay, so for example, when D is less than 2 and omega is positive, the bare one is bound, and let's say sigma is positive, so you get screened to Coulomb, but the resulting Coulomb is still bound. It's still dielectric. There are no free charges. On the other hand, over here, this is an interesting case. Omega is positive, so the bare one is a dielectric. Things are, charges are bound on short scales. But then I get the screening. But once I screen, I get Coulomb. But if D is bigger than 2, that Coulomb is 1 over R, and 1 over R is a plasma. So it's not, charges are not bound, so you really have a plasma. So then what would happen then? You'd have Debye-Huckel screening. Back to, to Yukawa screening. Okay, so that's why these are important. So let me go through some of the special cases. So again, I already mentioned some of these, or most of these I already just mentioned. So positive sigma means I screen. Positive omega means the bare potential is binding. And D less than 2 means the screen potential is also binding. And so this is what you have. This is kind of the main result that I advertised. And notice I wrote these powers as positive upstairs because they're both positive by this assumption. Okay? And so this is the main picture. So I have the screening and it goes to Coulombic from supercoulombic. And then it turns out, and we're still trying to understand this, but once you get to this guy, there's actually a phase transition. As a function of temperature, this guy can actually have binding-unbinding transition of a new universality class, very much like Hastellas-Thales, but now in dimension that's not necessarily, in dimensions that's less than 2. Okay? As indicated here. Okay, suppose a very special case of interest to people is, D equals to 2. Well, it's kind of the same thing as before. As in the previous slide, you go from r to the omega, positive omega, to Coulomb, but Coulomb is log r, and this log r now can then undergo a Hastellas-Thales transition of unbinding pairs, okay, into a plasma that's well familiar. So, this is quite a striking result. I give you this potential, and so naively you would say, without this screening, thinking about screening, you would say, oh, this potential cannot compete with entropy. It's never going to have a Hastellas-Thales transition. And what I'm saying is, going on a limb here, maybe somebody will say, well, wait, you missed something and there's an error in logic. But what I'm saying is, what we're claiming is that you start with a potential, bare potential like this, and what you discover is actually it does have a Hastellas-Thales transition, despite being, stronger than Coulomb, than log. Okay, in 2 dimensions, it has an unbinding transition. Okay, and then we actually calculate what the transition temperature is. Usually, Hastellas-Thales transition temperature is determined by the exchange, J or K. Here, it's actually determined by the core energy and this exponent sigma. And that's because it all has to do with the screening. It's dominated by the behavior of the screening length. And the screening length is determining how, polarizable these charges are. And their polarizability depends on fugacity and the core energy to create these charges. To create the screening. Okay, so it's very different temperature than the conventional Hastellas-Thales temperature. So if you're D greater than 2, this is the case I also mentioned. This is the picture, so it's a little bit more complex. You still go from the positive power, but now you go to the negative Coulomb power, meaning it's not confining. But now you don't stop here because now this is a plasma, and that plasma can screen using Debye-Huckel of a conducting screening, and so then this is standard Debye-Huckel screening. So you go from super Coulomb long range to Coulomb to Yukawa. The other one, as I also mentioned, sigma is less than 0, then you don't screen. And then, it just stays the same, and it depends on sigma. Okay. But sigma is negative. Well, the final one is final one I'll mention, omega is negative. If omega is negative, that means even the bare one is really doesn't, my calculation that I presented where you screen by dipoles is incorrect. Okay. It means, you really have free charges at finite temperature. If you have free charges, then you immediately have Debye-Huckel screening rather than dipole screening. If you wish, the susceptibility is infinite in that case, and indeed it is. If you try to calculate, you get divergence. In the Sine-Gordon language, what you discover is the cosine, rather than being irrelevant, is now relevant. So the charge is unbound, so then you get very quickly to this Debye-Huckel through that analysis as well. Okay, so now let me return to maybe something that's closer to the interest of this conference and the workshop is, XY model or ON models, but in particular focusing on 2D XY model. And this is actually what motivated me. I had been listening to talks and reading papers, a few months back when this project started about, spin systems like this and people making conclusions about what the long scale correlations are like in the system. And, what dawned on me is that, well, actually this guy can be written as, some XY model in the continuum, and it has vortices. Vortices have Coulomb-like interaction, and I know vortices can screen. So depending how vortices screen, you could have different behavior, even though if you start out with some non-zero J, eventually you have vortex screening create unbinding. If vortex unbind, you change correlations, spin-spin correlations. And so my thought was, well, then people look at long-range interacting, no, this is purely short range. I'm just reviewing short range. Yeah. Yeah, this is the nearest neighbor. So this is what motivated me, because I thought, well, maybe I now, because of this kind of argument, I'm going to prove that all those analyses are somehow wrong, that there's a screening length in these models, just like I showed you for the Coulomb, for the plasma models, super long-range plasma models, and therefore beyond some screening length, it's actually, there will be Kossler-Salas transition, there will be a modification of, actual behavior than what the bare exchange tells you. Okay, through this argument. And through this argument, you get this grad phi squared, then you can dualize it and get plasma, two-component plasma with a Coulomb 1 over q squared, and you can get to a standard Sine-Gordon model. And then using the arguments, do RG and screening on this and predict for the short-range models the connection between this model, and this model, they behave the same way. So now the motivation was, let's look at the long-range model. And I thought that this thing, again, will be connected to these two behaviors. And if they are, since I understand by the theorems that I described, that these guys then always screen down to 1 over q squared, to the Coulomb one, namely for positive sigma, then it must imply something about the exchange models, the long-range exchange model. Well, sadly, or maybe happily, if you're the author who's been studying these things, this doesn't happen, and this connection is actually broken. And indeed, you cannot go from here to here, and it has to do with basically, if this thing is at all long range, longer range than Coulomb, then this connection basically breaks down. Okay, and I can't, I can give you some intuition for it. If I have vortices that that are going to be described by this super Coulomb gas, then if I think of the vortex configuration phi in here, first step I need to do is I need to Taylor expand this guy to grad phi squared, or some long-range version of that. But I cannot do that, and you can show that it's because this kernel is so long-range, it forbids you're really summing over all r and r prime, and it forbids this Taylor expansion if this alpha is bigger than the Coulomb one, d plus 2. Okay, so this connection is broken. So everything I told you about these models is correct, but it does not overturn any results for the long-range exchange models. Okay, another way to see this is actually a complementary way is this classic paper by Fisher, Ma, and Nickel in 1972. They just said, forget this description in terms of so-called hard spin model. Let's think about a Landau theory. So, you approach it from the disordered side, and they wrote down a phi-4 theory like this for the ON model, but now the exchange is no longer q squared, it's q to the 2 minus sigma. Naively, it will be connecting to the, it's the continuum version of this model, soft spin version of this model. Well, they analyze this model, and it has, these classic results. When sigma is between 1 and 2, it's truly long-range mean field, so it's really trivial. It's just a long-range version of conventional mean field. But when sigma is it's too long range, so mean field dominates. When sigma is between 0 and 1, it's long range, but still critical. So the fluctuation is important. You have to do RG. RG is done in terms of an epsilon, which is, usually it's 4 minus d, but here it's 4 minus 2 sigma minus d. When sigma is 0, it's 4 minus d. But now its upper critical dimension is lowered a little bit. Okay? And in 2 dimensions, it's 2 minus 2 sigma. Anyway, so the key observation is that in 2 dimensions, this transition is completely standard. It's not Kostelis-Thalers. It's standard paramagnetic-ferromagnetic transition, but just with these exponents. Exponents controlled by this epsilon. So it's a Landau-like transition that these guys completely characterize. So that's another way to see that this connection in the result presented breaks down. Okay? And there's long-range order, as opposed to, if it was in XY model, we'd have a quasi-long-range order. Okay, so with this, let me summarize and close. So I talked about so-called super Coulomb gas with interaction that's longer range than Coulomb. Think of a dielectric with a binding potential. This is the model, and then I presented 2 types of arguments, the dielectric screening argument and Sine-Gordon screening argument. RG kind of argument, which completely agree and predict the screening length beyond which this kind of interaction crosses over to a Coulomb interaction. I discussed various cases, and I also showed and argued that naive application of this to long-range exchange XY model breaks down, and in fact, in this there's no screening. Okay, and with this I'll close and thank you for your attention.
I agree with your conclusion that you cannot map the XY long range on the Coulomb gas, but maybe also motivated by what's happening from the 3D XY and the mapping individuality, there is a generalized Coulomb gas in which the QI are not just charge, but have an index mu, so they are vectors. So maybe there is a generalized Coulomb gas. Do you have an idea of what generalized Coulomb gas could be?
It's a good point, but at this point I have nothing to say about it. I thought a little bit about it, but not enough to speak publicly about.
Yeah, so I want to follow up on my question from before, because also looking at the other slides, I could not understand this, the case sigma equals d minus 2, because it's all to all, so you can't have screening, because you can't reintroduce a scale.
You want sigma to be d minus 2?
D minus 2, exactly. I mean, if you just imagine you put, a charge pair plus minus into a system with this kind of interaction, then all the other contributions cancel out, yeah, and you're just left with a distance-independent interaction. So you cannot have screening in that case. And maybe that's a special case, but then I'm somewhat surprised that there's no indication of this as sigma kind of approaches d minus 2.
Right. Okay, so d minus 2, if you want screening, sigma has to be positive, so d minus 2 has to be positive. And so that means bare potential is not confining. Yeah. Okay, I don't know what, I'll need to think about it. I don't know off the top of my head. But your argument is that it's all to all, so it shouldn't screen?
Yes. Yeah. If it's all to all, you don't have a length scale, so you can't introduce xi. It can't pop out of nowhere.
Yeah, no, I need to think about it. I don't know. That's a good question.
Hi. Thank you for your talk. I found it really interesting, but I wanted to say that, I mean, there is some paper from me, Andrea, and Nicolò, which analyzes, it's very similar. We arrived to very similar conclusions about these, I mean, we start, let's say we do the opposite journey of your talk. We start from the XY and the Villain model, which is a sort of Coulomb gas with longer range interaction than Coulomb, let's say. And those results are, our results are really similar to yours.
But I would say that mapping, one of the points is that mapping is not.
That's one of our results, yeah.
That mapping is not.
Yeah, that's one of our results. The mapping between XY, the real XY model and the Coulomb gas no longer holds for longer range interaction. But we studied this Villain model, which is a simplified version of the XY, which is always mappable in a Coulomb gas, and we showed that it's in a different class of universality than yours. And also this Coulomb, this Sine-Gordon screening argument. But what we find to answer also the previous question, is that for when the exponent is large enough, small enough, when the interaction is sufficiently long range, you have like a breakdown of your argument, dipole argument.
Right.
That's a bit hidden in the calculation. I don't think we pointed out clearly as well, but I think it's the.
Well, for us, it breaks down when sigma is. Sigma has to be below 2.
Sorry.
My sigma.
Our sigma is probably a bit different from yours, but I think when the we worked in 2 dimension, and we show that when the exponent of the interaction is less than 1, then I think this picture breaks down. But I mean,
yes. So I also have, I define sigma slightly differently, or it shifted relative to yours, but I think it's your 2 plus sigma, I think, is the same as my sigma. But the point is, I also have limits on, on my sigma. It has to be 0 to 2, I believe.
Okay.
Yeah. So I also have some.
But anyway, it would be nice to.
Otherwise, it's not. Energy is no longer extensive.
Yeah. But apart from before this happens, there is another breakdown of the dipole renormalization group, but I think we should continue maybe in private. But
Sure,
I found it really interesting because there are very similar results to ours, but rephrased in a different language.
Okay. Well, I'd be like, did you guys calculate this crossover scale?
No. That's what I mean. Since we were more interested like in the critical properties in the phase diagram, we didn't actually compute this physical scale, this crossover scale. But I think it's worth talking about that.
Right. Yeah. No, I learned about your work from the talks at the workshop. Our work has been going on for a while now, but I first heard about it in this workshop. So it was very nice. Yeah.
So thank you, Leo, for the talk. Yeah, I also wanted to add that. So we have worked quite a bit with Guido, yes, on the Villen model, but also on the what you call the soft spin model. That you say it's true that different universal class, but I wouldn't say that Fisher and Ma had fully described the transition. So not just us, but a lot of people have worked on it, and we find that.
I would say, I would think they're the first ones that studied it.
They were the first ones, but you say at some point you say that they fully described the thing, but I say that there's been a lot of work that was going on about this ferromagnetic transition, the sigma star, not just by us, also like just following Fisher and Ma. But apart from this comment,
I think in a controlled calculation in the epsilon that they introduced, I think that's in a controlled calculation. What they did is I don't see any corrections there. You can go to higher loop, but these things
don't you think that the results by JSAC are controlled? I understand that you don't like our method, so let's skip our result. But even so this we can discuss.
Well, I think some of it is okay. I don't think okay.
But also the paper from JSAC of 73, you wouldn't call this a control calculation?
Yeah. Okay. I think let's leave it. No, so I know it from your talk, and I'm still trying to come to a conclusion about that, and it makes me a little bit.
Okay, but let's all just acknowledge that. So I said it's not just about our method; these were results that also people were
I referenced the first paper on the subject. So, I think it's fair.
That's true. Right? But I had a real question, like concerning because we were talking about lower dimension and Kosterlitz-Sauer. So I think in D equal 1, and your sigma, what would be the Kosterlitz-Sauer 1? So for me would be sigma equal 1. For you would be something different. But so I think there were papers on like sine Gordon with Q in D equal 1.
Yeah.
So
this is the usual. Kosterlitz did first Kosterlitz calculation is exactly that model.
Well, it's a Ising model with 1 over square, but I didn't think it. But he didn't think he mapped it to the sine Gordon, did he?
Well, but no, I don't. Not sine Gordon, but I think it is Q mod. It is mod Q in Fourier space. So it's 1 over t squared, and 1d it's mod Q.
Yeah, but I wanted to see if your equation were giving still only 2 phases. I wanted to ask if you checked that linear Q, so Q to the 1, sine Gordon in D equal 1. Gives you 2 phases or more than 2 phases.
Oh, I see.
Because this, I think, it's a bit debated in the.
Okay, we're still thinking about it. Actually, right now looks like I would say from this argument, from the argument of standard, the argument that I gave, or the picture that I gave. This guy, I would say there's only 2 phases. Oh. But Beyond that, I'm still thinking about what are other possibilities. For example, in this case that I mentioned, the Coulomb binding transition in this case. So for D less than 2. Okay, but
sounds like a delicious topic for discussion over coffee. So I think without further ado, let's thank Leo.